Well, good morning, and welcome to this Conservation Applied Research and Development webinar. I'm Mary Sue Obenstein, and I'm the R&D Program Administrator at the Department of Commerce, Division of Energy Resources. And with me today is Mark Garofano, who is Energy Engineer at the Division of Energy Resources. Could you turn to the next slide, please? Division of Energy Resources, where he performs engineering reviews of custom efficiency projects and leads the department's efforts to maintain and update the Technical Reference Manual, or TRM, that utilities use to calculate the savings and cost effectiveness of their conservation programs. Mark is helping me out today with by leading the Q&A section of the webinar. And as the TRM lead, he'll also be able to answer any of your questions related to inclusion of the technology we'll be talking about today in the TRM. Our topic today is demand control systems that deliver efficiency and service hot water systems of commercial buildings. Our presenter is Ben Schoenbauer from the Center of Energy and Environment, where he is a senior research engineer. At CEE, Ben conducts research on new and innovative technologies and ideas dealing with residential and commercial energy efficiency. His work includes identifying new opportunities, conducting field research, identifying and pursuing funding opportunities, and disseminating the results of research that he's conducted. Ben's areas of focus include water heater performance, service water heating, residential HVAC systems, and beneficial electrification. This webinar is one in an ongoing series that's designed to summarize the results from research projects funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. The purpose of that fund was to help utilities achieve their 1.5% energy savings goal. Of that fund, about $2.6 million is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Results from CARD projects provide utilities with informative and timely information to enhance energy efficiency program designs within their SIP portfolios. In turn, SIP helps to conserve energy resources while reducing harmful emissions, minimizing the need for new utility infrastructure, and generating positive economic value for Minnesota citizens. Projects funded to date by CARD have quantified the savings, cost effectiveness, and field performance of advanced technologies, or characterized market and technical potential of products and technologies in the state, or investigated and piloted innovative conservation improvement program strategies, and performed other research on other issues related to the fund's purpose. As you can see by the pie chart, CARD projects to date have been in all building sectors. And as I mentioned, the subject of today's webinar is in the commercial sector and details Ben's evaluation of demand-based controls for central domestic hot water systems with recirculating loops. Now I'm going to turn it over to Ben.
Thanks, Mary Sue. Before we get started today, I want to touch base and mention some of the partners that we had on the project team that won't be represented or won't be speaking today, but were very valuable in completing the project. So first off, we had the Gas Technology Institute as a partner on this project. Their efforts were led by Mary Sweeney and Alejandro Guda. We also had Alex Hanar from CE and Gabe Ayala from the Innovative Group that all worked on this project. So first of all, I want to start by giving a brief introduction to what is demand control recirculation. So this is a control strategy designed to reduce the energy waste in central domestic hot water heating systems. These hot water systems in buildings really keyed at the non-residential sector, so larger buildings including multifamily, office, schools, hotels, etc. So they're all we're looking at this controller that's really targeting that market. Often these systems in these buildings are one big central system, so you have one large heating plant and a distribution network of piping that connects all the fixtures throughout the building. And they do this in order to have hot water ready at all times, but it often leads to long insulated plumbing runs with constantly recirculating hot water. This demand control is a type of control that reduces the waste the energy waste there without impacting the hot water delivery of the system. And these systems can reduce the pumping energy, the energy for the pumps, as well as the thermal energy lost through the plumbing and other parts of the system. These controllers can actually sense when hot water is being used in the system in order to reduce that waste and optimize pump runtime. The diagram here at the bottom of the screen shows the three major components of this controller. So you have the central sort of demand controller apparatus that integrates with the circulation pump in the system. And then you have two sensors that are placed into the system. A flow sensor to really look at when that hot water use is being activated, as well as a water temperature sensor on the return line so that you know what the temperature is in the loop. So continuing on this discussion of the controllers, sort of how does the controller actually work in operation? So when the controller is on, by default, the pump is off. So this is sort of a change from your normal system that's circulating hot water 24 hours a day. With the controller on, the pump is normally off. And then as the building uses hot water, this flow sensor senses hot water use in the system. That's step number one. When it senses flow, it then checks to see what that return water temperature is, or the water temperature coming back from the recirculation loop. If that temperature is hot, then the pump stays off. The system's getting the hot water it needs. Everything's good to go. The pump doesn't need to run. If that temperature is below a target temp, then the pump turns on and sort of reheats the system, gets that hottest water back out to all the fixtures, and gets the loop hot. In addition to that normal operation, there's also an auto prime feature so that if the system temperature does drop below sort of a minimum threshold, the system is reheated. And the pump runs for a short pre-programmed time period in order to prevent any long-term temperature reductions. These controls have pretty significant benefits compared to some base type strategies. Other control strategies that have been used are timer-based or temperature-based controls. And these controls can reduce waste, but limit the savings potential because they don't know what the actual demand is in the building. So the demand benefit here are really that it can sense when there is hot water usage in the building and react in real time. So if you think about like a timer control, the drawback is that you have long delay periods overnight where you're not heating hot water where the system is allowed to reduce the set point, and then somebody wants to take a shower in the middle of that period and they have cold or hot water. Whereas this controller senses that use and keeps the water hot for them. The other big benefit here is that it also has that temperature controller, and so that it can really tell when the system needs hot water and limit use in multiple ways. So the next thing I want to say for this project is that we're really building on past success. So this controller, as I mentioned, was designed for sort of any large-scale hot water central system in buildings, and has been tested pretty extensively in multifamily buildings on both coasts, mostly in California and New York. In multifamily buildings, California code and program design strongly encourages these controls. So they've seen quite a few systems installed and also had quite a few systems studied with full monitoring projects. And so we can see some of the benefits there and sort of try to move that to this climate and then look at also expanding the scope by focusing on commercial buildings and hospitality buildings in this project. So thinking about those past studies in multifamily buildings, we've seen 90% plus reductions in the recirculation loop runtimes. That's reducing the pump runtime from 24 hours a day down to 2 hours or less per day. So you're cutting that pump energy pretty drastically. And by doing that pump reduction, those buildings saw on average a 10 to 30% reduction in the thermal energy used for domestic hot water. So that's if your water heater uses gas, that's 10 to 30% of the gas consumption of the water heater is reduced. For a mid-sized multifamily building, that's an average of about 1,400 therms per year and about 750 kilowatt hours per year, or a savings of about $1,300 per year. So it's a pretty good amount of savings, and we wanted to look at how that would reflect Minnesota buildings and this larger commercial building population, because the systems in those commercial and hospitality buildings are very similar, but the usage profiles do tend to change. So for our Minnesota field study, we had a couple of phases. We looked at 17 different central DHW systems for our first phase, where we did site visits and surveyed those sites. We also then did preliminary monitoring on 10 of those sites, where we did a short-term look at how often the pump is running, look at what the thermal losses are off the system. I did that for a couple of weeks in 10 sites. Then from that information, we selected 6 sites that looked like good candidates, or typical candidates for Minnesota buildings, and we collected data in those sites for 12 months, alternating performance between the baseline mode and the new controlled mode. So at the bottom of the screen, you can see the summary of the 6 sites that we did put in monitoring equipment in. We had 3 hotels of sort of a range of room types and sizes. We also had 2 education buildings from the commercial sector, so these are classrooms. One of those mainly served the sinks in the classrooms and the bathrooms, and the other served some sinks as well as some larger locker room and shower facilities. And then the third building type we monitored was a more standard office building that had offices and bathrooms on the loop as well. So I want to talk a little bit about that first phase of monitoring, where we went in and surveyed a handful of buildings and some of the things we learned about Minnesota's buildings and the characterization of them in thinking about hot water systems. So all the systems we looked at ran continuously 24/7 in hospitality buildings, in hotels. One system did have a temperature-based controller installed on it, but the control parameters had been set such that the system never actually turned off. So essentially, at some point in the operation of this building, a building manager had decided that they didn't want to deal with the controls, and so they just set the temperature so high that the pump never turned off. None of the active building operators at that site had any idea that there was a control system set up on that loop, and they had all just assumed that it ran 24/7 no matter what, which it was in practice, but in theory they could have been doing some control. Big thing to point out here is that the system complexity scaled with size. So smaller hotels, less than 5 stories, had pretty straightforward recirculation loops, and smaller pumps with about 3/4 horsepower or less. Larger systems were more complex. They had bigger pumps. They had occasionally had booster pumps if there were too many floors for the city pressure to provide water to. Lots of times they have multiple zones. And we'll get more into some of the details of these complex system types later in the presentation. One additional detail for the hospitality sector is that occupant satisfaction is by far the highest driver of anything mechanical, HVAC related in these buildings. And so they were the most concerned about people having hot water. The cost of that hot water really didn't matter to the actual building operators. The owners, the cost mattered a bit more to, but in terms of what is your deliverable at the end of the day, it was really just get them hot water at all costs. And so there's some additional sort of feedback or discussion you need to have with those types of operators. Moving on to schools, they were a little more likely to have some control, but most ran with some sort of time of day controls. A couple were on continuous, but most of these buildings were assumed to be unoccupied overnight, and so they had the systems shut down and not circulate hot water for some periods of the day. On average, the systems ran for about 19 or 18.75 hours per day with a kind of 4 or 5 hour overnight shutdown. A lot of these systems were small and concentrated, so they had fewer loops that ran to a relatively small number of fixtures in the building, but those fixtures varied greatly. So you have everything from locker rooms, bathrooms, kitchen and dining facilities, as well as a lot of sinks spread throughout the building, and classrooms and kitchenettes and break rooms and those sorts of things. So lots of variety of uses in schools. And we also had some more complex systems that we'll get into as we continue to move through the presentation. Commercial buildings, again, here about half of the system had some time of day controls, and they ran for about 16 hours per day when controlled. And so you can see they're starting to control a bit more here, assuming that nighttime period is longer. We'll note that anecdotally, a couple of the building operators noted that they had to change the time of day period pretty substantially based on the hours of occupants, and as little as one occupant deciding that they were going to come to work at 5 in the morning required them to shift that time of day period if that worker tended to be someone that used hot water and let people know when it was cold. So it's something important to note is that if you have a controller set up that's sort of time of day designed, if as little as one occupant in a huge building has a change in how they use hot water, it might impact the controls for the whole system. Large buildings, here in this sector, there's lots of different building types with a variety of system design. So the end use is pretty similar in most of the commercial buildings we looked at, but the actual hot water system and its design had a lot of change. One thing we noted here, again, larger systems were more complex, but we also noticed that the building age had an impact on the complexity. So a building that had been around for a long time was likely to have changing occupants and changing needs over time. So maybe they've moved where the bathrooms are, or they've added a kitchen or something like that. And so the hot water usage have slightly changed over time, and so that impacts the loop types in the building. But also with changing sort of boilers or water heaters or things like that, the hot water sources may have changed over time as well. So I want to take a few minutes and walk through what the actual installation of this controller would look like. Again, as I mentioned earlier, there's sort of 3 basic pieces to this install, and they're highlighted here in this diagram. Starting with the flow sensor, you can see in the picture here is on the cold water inlet to the tank. It's highlighted sort of at the top on the right-hand side of the water heater there. It comes in a pre-fit tee from the manufacturer, but can be installed in a variety of ways depending on your system type. And that goes on the cold inlet to the water heater so that you can see any sort of hot water use in the system will be measured by that flow sensor. That flow sensor is connected into the controller, which interacts with the pump. And so you can get that system performance captured there. The next piece then is that cold water temperature. You can see that on the bottom of the picture. That is a strap-on temperature measurement. And the manufacturer found, and I think this is common for not only the manufacturer we work with, but the others that are available on the market as well, is that a surface mount temperature is accurate enough and fast enough responding to be an effective measure for the system, so you don't need to cut into the plumbing system in order to install that sensor. Which you do need to do for the flow sensor. You do need to cut into the system to install that sort of immersion type sensor. So once these sensors are installed, then the controller can work to regulate the pump. I should also note that inside that little control box on the side of the water heater there are 2 settings that can be changed on the controller. One setting controls the return temperature target that sets sort of what that minimum temperature is in the loop. The default temperature setting is about 98 degrees. That temperature is representative of the sort of hot water delivered to the last room on the line. So ideally, that sensor is placed as close to that location as possible. but typically installed in the mechanical room just for ease of access. The second control point has to do with the deadband, or how far between sort of the hottest and coldest temperature allowed in the loop, or how big that temperature is allowed to drift. For our field study, we installed some extra instrumentation, as you can see in green on this chart, as compared to the couple of sensors that are installed from the manufacturer in pink. So we added in a flow meter. We added in some additional temperature sensors, both on the inlet and the outlet of both the full system as well as just on the recirc loop. And then we collected information on the runtime and power consumption of the water heater itself and the pump, so that we could really characterize the energy consumed by these systems and the energy delivered in both the baseline and the controlled mode. And then we could compare those system performance pieces. So before we get to the savings, I want to talk a little bit about how the systems were operating prior to control. So as I mentioned, most of these systems were either on 24-hour-a-day constant recirculation, or were constantly recirculating for the majority of the day with some overnight setbacks. These systems had pretty high water temperatures being delivered, and the system loops were pretty high capacity. And all the temperatures when running at constant circulation and capacity and availability were pretty constant. So things stayed hot and stayed consistent in the operational mode. On average, there was a 15-degree temperature drop in the loop during idle. So when no hot water was being used in the systems, the temperature dropped from delivered out to coming back to the mechanical room by about 15 degrees. In some cases, that temp drop was as high as 30 degrees in one case, which is a pretty big temp drop just for recirculating hot water. And that's due to the kind of the speed of that recirculation, as well as the length of the loop and the plumbing type in the loop. In many cases, these high temperatures and high flow rates in the system can lead to larger and larger losses off of the loop, or you have to supply more heat to keep that loop warm to get out to all the fixtures. About a third of the system, systems that we measured had return temperatures that were 125 degrees. And so if you think about how you use hot water, you typically don't use water as hot as 125 degrees. Something closer to 100 to 105 degrees is more typically used for hot water uses in buildings. So having a coldest possible temperature in your loop of 125 degrees is probably excessive heating. And so these sorts of things match up with some of the cases that we sort of our best practices cases for multifamily. And so we expected to see the 10 to 30% total loop losses that we saw in those multifamily buildings. And when we get to the results, you'll see we fell within that range for what we actually measured for loop losses. So continuing on, I wanted to kind of look at some of the data that we collected. So here's a system curve for continuous operation. And this is about 2 hours of operation in one building of one day. So this is just a random snapshot of a period of time when there was relatively low hot water use and the pump was running for 24 hours a day. So you can see the hot water use in the gray here, and that goes to the axis on the left hand of the screen. So it's kind of between 0 and 5 gallons per minute. And for about the first hour, it sort of goes somewhere between 0 and 5 gallons per minute. I was using some hot water in the building. And then the second hour of this period, you see that the hot water is basically turned off. And what we notice during that period is that the red line, or the hot water temperature out to the building, and then the purple line, the recirculating temperature coming back from the loop, are pretty consistent throughout that period and don't change much at all. The supply temperature is something like 130 degrees or 135 degrees, and the return temperature is something like 127 degrees or so. So we have this sort of pretty uniform performance. The one thing we'll note is that when hot water is being used in the building, you can see that blue, that makeup water temperature drops as the cold water comes in to make up for that hot water being used in the building. When we switch to the controlled operation, or when the controller was active, when we see sort of similar hot water use between 0 and 5 GPM sometimes, but mostly off, we can see that supply water temperature again is pretty hot, around that 135 degrees, but we see that the return water temperature is quite a bit lower in these cases. So it's right around that 107 degrees that the controller is set to allow, or 110 or so degrees that the controller at this building was set to allow as the minimum temperature. And you can see that throughout this period, it's periodically turning on to maintain that minimum water temperature in the system. And again, you can see the cold inlet temperature decreasing and dropping down to that makeup temperature around 60 degrees when hot water is being used in the system. And so you can see that the pump time has been drastically reduced here, which has an impact on that return water temperature. And so as we go through the analysis, we can see the impact of that reduced pump energy and reduced temperatures on the full performance of the building. And so here's a look at the thermal energy use between the two modes. And this is a sort of daily numbers for one building. This is one of our commercial sites that we monitored. And so you can see on the x-axis we have the energy delivered in hot water per day. So that's the gallons of hot water used times the temperature difference that we see that we have to reheat, and the thermal use, or the energy use by the water heater in this building. And so the big takeaway here is that in almost all cases, or in all cases, the controlled data, the red data on this chart, is using less energy for the same number of hot water gallons delivered than the blue, or the 24/7 data period. So the controlled mode is consuming less thermal energy per delivered BTU than the 24/7 operating system. One thing I will point out is that there seems to be some offset in how much usage is going on in this building, and that is partly due to the inlet water temperature and the time of day that was the system was being run for. And so our analysis corrects for that. And if you're interested in more on how that works, the final report will be out soon, and that goes into a lot of detail on how the analysis sort of looks at these differing usage patterns because of time of day and seasonality concerns for the two different modes. Moving on to the electrical use, again, you can see the controlled data in blue, or in red, sorry, and the 24/7 operational data in blue. And here we have on the y-axis, we have the sort of average watts per day used in the two modes. So one thing to point out is that this site had a pretty good ECM pump. So even when the pump was running 24 hours a day, it was only using sort of 80 watts for 24 hours a day. So that isn't a huge energy consumption. And there's, despite the fact that we're reducing the average daily consumption to about 10 watts per day in the controlled mode, that's a 90% reduction, but it's still not a ton of power consumption. But in a building that had a less efficient pump and higher pump energies, that would be more significant. Another thing that we looked at in terms of performance was the recovery period. So if we're allowing that pump to turn off and then asking it to recover when there's a demand, how long does that pump take to reprime the whole loop? And so this is a sort of an extreme example. So we have a time period here that we can see where the temperature was allowed to drop to a minimum that's under 90 degrees. We got about 85 degree temperature. This is the return temperature coming back from the loop right before it re-enters the water heater. We've let that drop all the way down to 85, and then we trigger a demand and try to ramp the temperature back up to its minimum set point, or not minimum, to its set point of around 115 degrees. And so in this case, it took about 35 seconds to do that recovery. That can be considerably longer depending on the flow rates and the system time. It can also be shorter if the minimum temperature is set higher. So if you only allow the system to drop down to 107 degrees instead of to 85 degrees, we can change these recovery times. And so that's something that needs to be dialed in for a specific building. And this, as I said, this is sort of set up to the extremes of the controls for this setup, but can be changed as you install the system. A couple of additional points for thinking about this controller in terms of a program development or program runout. Opportunity identification is sort of thinking about where this technology works and identifying these opportunities before you have to do this detailed monitoring or even short-term monitoring. So as I mentioned, these systems are really designed for large central DHW systems with constant uncontrolled or majority of the day constant uncontrolled recirculation. The systems also need to be large enough so that the energy use and waste is big enough to be practical to target for an energy savings demand or to spend time and money to target. And I'll get into that as we get to the results, but something to keep in mind as we talk about how these systems are set up. Installation, for most buildings, installations are straightforward and ready to go, and you can kind of take things right out of the box and install them without much issue. In larger, older buildings, the installs can get more complicated, and is something I'll spend some time on the next few slides here. But installing the equipment, setting those parameters, and integrating with the actual system in the building can be less straightforward in some more complicated systems, and something that kind of feeds into how this technology might be rolled out on a larger scale. Then also a few things that want to be done to ensure that the system operates well and as intended. And making things like making sure that the building staff understands how the controller is working and how to adjust things should issues arise. This, as I mentioned, this controller is demand-based, so it will react to the usage in the building, which is good. It limits sort of the need for intervention from building staff. But in the past, controllers often have failed to work because nobody knows how they work, and it's easier to turn them off than to ensure that they're working correctly. So that's an important point to remember as we move through it. So I mentioned a couple times that we would look at some specific installation examples from the sites that we monitored, and I want to kind of go through some potential things to be aware of that sort of take us away from that simple installation case. Also some highlights for what you see when you get an easy case, and some things to think about as we move towards what the future of this controller could look like with improved technology. So first off, here is a system where the system age that I mentioned can really come into play as for how the installation might go. And so this is a system that had a large indirect tank that was actually on a district steam system. So it had a hot water steam, not hot water, but a steam heat exchanger in the indirect tank. But this indirect tank was pretty old, and so the cold water inlet that you can see entering on the bottom of the tank here was old cast iron piping with little or no shutoff valves in the system. And so our typical flow sensor location of the cold water inlet was a tricky one to handle on this system because of this lack of shutoff and the idea that integrating a newer plumbing fixture like the T for this flow sensor with this old cast iron large diameter pipe was not a great idea. And so the controller is able to be installed on the hot water side without much change to anything, but it's something that is sort of not the normal practice, and so a flexibility that is necessary when installing these systems. As I mentioned, additionally with the no shutoff valves, you have to be aware of, sort of how the system can be isolated so that cutting into the existing plumbing has the least impact on the system. And so that was much easier to do on the hot water side of this system because it had been replumbed more recently. So otherwise this install was pretty straightforward, but those were a couple of issues that arose and had to be handled, and flexibilities that were needed. Another interesting installation was one with multiple water heaters. So we saw this a lot in the hospitality sector, where the system will look much like the traditional typical system that I showed earlier, but we'll have several water heaters either in series or parallel. And the important thing here is just to install the sensors so that we treat the trio of water heaters like a single water heater, and so that the flow sensor is installed in a location where you can see flow, where it can see flow from all the water heaters, and so that no hot water use is bypassing the flow sensor. And this installation became somewhat tricky to integrate our controller with all the other existing equipment because they had a large softener system on the inlet to the system. And so the easiest installation here was actually to install multiple flow sensors in series with one another so that we could tell when each of these water heaters was firing. So that was a pretty straightforward installation as well, but again, just something to be aware of is that how these sort of additional features in an install may impact the installation, and just being able to think through those minor changes. So here's an example of changing heating sources and potentially failed boilers or heating supplies that have been replaced with other systems, and those changes over time adding to a more and more complex water heating system. So this is pretty common in older buildings where the intended use and system design has changed over time. And so this is sort of comes up trying to kind of prioritize or limit the amount of downtime for the system. And so they've added sort of a backup hot water boiler or a backup heating source that can keep the system hot while the primary source is being worked on. And so it sort of can add to some sort of complex plumbing connections and heating zones and different things like that. And so we also found that it's not always the case where the operator totally understands how these systems are operating, or where the flow is going, or where the loops are going, or which pipe is which. And so being able to trace that out and understand things is important, and being able to ensure everyone that the system will run well and that they know how to control and operate it. So this site is actually one of the 6 sites that we installed, and we were actually ultimately had very limited data on the system control in the controlled mode, both due to it taking some added time to get this system up and running because of the complexity, but also because the building actually changed ownerships midway through our project, and the new owners and operators couldn't really figure out how this hot water system was working, and so they were uncomfortable with having us make changes to it when all they knew was that it worked, and they didn't want to make it not work. And so we had some difficulties with this new building owner ensuring them that they could do this without any issues. And the last area I want to touch on the installation complexity is sort of the system, how it's working might be masking some potential issues in the system that installing a proper control can sort of unmask and can arise. And so the 2 issues I'm talking mostly about here are balancing within the system and crossover within the system. And both these issues can be hidden by severe overheating and lots of energy waste, And so when we reduce that overheating and energy waste, it can sort of unmask these problems. And so it's something that's not hard to check for, but something that we need to understand if we're going to roll out these controllers in a large number of buildings. So I'll spend a little bit of time talking through the basics of these, but there's a lot more information available about how to simply check and test these things and understand them. There's been some work in California that's shown that there's a decent fraction of buildings in which these things are issues, and that they were identified through rather short tests. That work hasn't really been repeated elsewhere in the country, so we don't know if that's the case here, but it's something to be aware of as we move forward thinking more and more about these systems. So at the top of the screen, the top figure is focusing on zone balancing. So with proper zone balancing, it can be done with sort of check valves or balancing valves in the system. So it's a case where you have a single pump, but you have multiple loops. So this can be like a multifamily building with 3 different floors, and each floor has its own loop. And as you move up through the building, you get more and more zones. If not properly balanced, you can see things like the much higher flow rate through zone 1 than through zone 3, just because that's where there's the least resistance. And so you can see something like 10 gallons per minute going through zone 1 and 2 gallons per minute going through the zone 3. And because you're supplying the same hot water to all of those zones, you can see pretty significant differences in the return water temperature from each of those zones. So in order to keep zone 1, in order to keep all the zones hot, you end up with a much higher temperature than you might otherwise. And so if you reduce that overheated zone to being heated correctly, you might have a further off zone that isn't being heated correctly. And so it's important to understand that those balancing zones are working well and in conjunction with each other, so that all 3 zones, when controlled, continue to supply good hot water performance to the building. And so that's an issue that can be uncovered if you install a controller. Similarly, similar things apply for the crossover condition as well. And so this is a case illustrated in the lower figure where it's essentially a failure of a mixing valve. So in a recirculation, a hot water recirculating system, you have this pipe with continual hot water flow, the lower of the kind of 2 big horizontal pipes in this figure. And on the left, when things are working well and there's no crossover, you can see the hot water flows from the hot water side and the cold water flows from the cold water side, and they mix in that shower head and everything's fine. When crossover is present, when the shower is off and that mixing valve has failed, you can see that you have, in this case, cold water flowing through that valve and into the hot water side of the system, and then that lowers the water temperature in the recirculation loop as you go forward. And so obviously a correction for that is just to make the hot water temperature higher, so that that sort of reduced or cooled off hot water temperature is still hot enough to provide enough heat to the rest of the building. So then if you dial in that hot water temperature with a control system, you can have implications further down the line. And obviously having crossover can be a pretty big energy penalty. And so just overheating the system isn't a good solution, regardless of whether that is the solution being used often accidentally. And so there are some pretty simple full building tests that can be done to do this. And those mixing zone valves failures are more common than you might hope for. So as I mentioned before, here's just sort of a picture of a good installation. Pretty straightforward, single heating source, single loop, with lots of good shut-off valves. And this is sort of the ideal case. Makes things quick and easy. These installs were taking sort of less than 2 hours by the time we finished with the installation. One thing I wanted to point out, we won't spend much time on, but just for a thought, so you do have to cut into the current state, you do have to cut into the system to put in that flow sensor. But there have been some pretty big drastic changes in non-intrusive flow meters over the recent years, and some big advancements in that technology. So these types of flow meters have been around for a long time, but are often very, very expensive. but that's a lot to do with them needing to be accurate. And the technology for just sensing whether there is or is not flow in these non-obtrusive matters is becoming much cheaper. And so adding this type of sensor would reduce the install cost and downtime. You wouldn't have to cut into pipes, and potentially you wouldn't need a sort of licensed plumber to do any of this work. But you could also add multiple flow sensors to really dial in and understand what was going on in the system. So there's some potential for some big advancements there as we move forward. I did mention as well that as part of our analysis, we really looked at sort of correcting for some of that seasonal performance and profile performance in the buildings, as well as characterizing the demand and the sort of demand of the systems and the thermal losses off the systems. And here's just some examples of that type of work in one of the sites. I won't spend much time on this here, and there's a lot more detail on this information in the report, but I wanted to show how that works before I move to a summary of the savings for the 4 of the 6 monitored sites. So I mentioned the one site that we didn't have a lot of data for due to the occupant being changed out. There was also a site that had sort of an atypical heating source. I mentioned it earlier, the steam heat exchanger system. And so those 2 sites had much bigger error analysis than the sites shown here. And so they're included in the final report in more detail, but I have similar type numbers as these. But I wanted to focus on these 4 sites because we have the most confidence in the data at these sites. And these are really very well characterized. So I want to point out a couple of things in these savings, in the savings slide, starting with looking at the actual energy savings or the percentage savings at these 4 sites. And so you can see, as I mentioned earlier, that kind of 10 to 30% thermal savings number we were talking about. We saw 13 to 19% thermal savings in these sites. So right in that expected range that we've seen in multifamily buildings. And we also saw sort of on average about 90% savings on the pump energy side. We did have one site that dropped down to only about 70% savings on the pump energy side. And those all come through about reducing that runtime from continuous down to something like 2 hours a day, or as short as less than an hour in the one education building that's shown here. I will say that the hospitality too, one of the reasons why the savings percentage is lower there than in the other buildings is because that building was the most concerned about occupant satisfaction, I'll say. And so they were by far the most conservative on the set operational set points that we used. And that probably had some impact on the runtime and the savings present there. So both those savings percentages are right in the range we would expect. The next thing I want to point out goes back to that identifying the opportunity point that I made earlier. And so that's really looking at, how much hot water is being used in these buildings. And so you can see the hotel buildings were up 2,000, 3,000 gallons a day, whereas the education and hospitality buildings were, 140 and 75 gallons per day. And so that not only impacts the amount of hot water used in the buildings, but also impacts the size and rates at which those systems are operated and the capacities of those systems. And so it really increases the actual energy waste. Bigger systems waste more energy than small systems. And so it does impact the sort of dollars per year saved. And so you can see that on the farthest to the right, that in those higher use buildings, we're saving up in that $1,300 per year range that we saw in those mid-sized multifamily buildings, in those hospitality buildings. But on these smaller commercial and education properties, the savings are a lot smaller just because the annual energy bills and consumption in those areas are much smaller. And so these are kind of the high-level summary data. As I mentioned, the final report that will be out soon will have a lot more detail on how those numbers were calculated. Here's just a look at kind of those numbers in another way. You can see the kind of dollars per year savings and the gallons per day being used at the bottom of the screen. I do want to point out that on this slide that for our installs, the controller cost was and labor cost, the whole package, everything was right around $2,000 from the time you bought the controller to when it's up and running. So it's a pretty good cost. So when you're saving $1,000 or more a year, your savings, your simple paybacks are less than 2 years. For that biggest building, it was less than a year. For the second hospitality building, it was closer to 2 years. And then when you look at the education and commercial properties, you have a much longer payback just because the usage is so low. So those buildings are saving 20%, but that 20% is only $200 a year. And so then in those cases, your savings are more like 10 to 20 years. So with that, thanks everyone for coming, and I think we have a little bit of time for some question and answers. I'll turn it back over to Mark and Mary Sue for that portion of the webinar.
Great, thanks Ben for your great overview of your research. And yes, now we're going to turn it over to Mark. We've got a few questions, and we are running a little bit late, so we'll probably run the webinar just 5 minutes over or so to try and get as many of the questions as we can. If you have a question and you haven't sent it in to us, send it in to us now so we can get it within that extra few minutes to answer it. And now I'm going to turn it over to Mark.
Okay. Thanks, Mary Sue, and also echo the thanks to Ben and the rest of his team for all the work they put together on this project. So the first question we have is, how many units is defined as the mid-sized multifamily building?
Yeah, that's a great question. So for that other work, they sort of did a wide range of buildings. They didn't do anything that was sort of, I guess for their purposes, they didn't look at anything that was smaller than sort of like 20-ish units, but they went up to these buildings that were in the, few hundred units per building. And those sort of 10 to 30% thermal and 90% pump savings were pretty consistent across those building types. The thing that the big thing that changes is that last kind of point that I made is sort of what your gallons per day is going to be drastically different in a 20 unit building than it is in a 500 unit building. So roughly those percentages are going to be pretty consistent, but how much energy is lost in those buildings, the number of BTUs and therefore the dollars saved is going to be pretty drastically different.
Okay. Next question is, what's the 2000 cost per controller or per site?
It was per loop. So yeah, I guess the one install that had the 3 flow sensors installed, that one would be more than that $2,000 range. I'd have to look back and get the actual number before I said one. But that's definitely an atypical installation solution. If that site hadn't had that softener really close to the water heaters, we would have just installed it upstream of all 3 water heaters, a single controller. So I think that 2,000 was a pretty good number for the time we were installing these controllers. I will also say I'm pretty sure that number is much lower in California, where they're doing these much more frequently. There isn't currently a good manufacturer kind of distribution network here. So we worked directly with the manufacturer to buy the controllers, and then worked with some contractors that CE works with a lot. And so that contractor now definitely has the most experience with these controllers of anyone in Minnesota. And so if a program was developed here and they started installing some more of these, that cost and the time to install these and the understanding of the systems, all those sorts of things I think would come down pretty quickly, as was the case in California for multifamily buildings. So yeah, so that $2,000 should be a per site or per loop install.
Okay. And actually I have a follow-up question to your question. That they were wondering why that will vary widely across water heater systems and building types.
It shouldn't vary too widely across building types. The only time it would ever really change is that case where you need additional hardware. which I think is definitely a minority of installs. And as I mentioned, I think it might come down as people understand the controller, the system types, and the buildings we have that would be applicable.
Okay, next question. Do you see this technology having a greater potential in the multifamily sector, where water demand varies, or large commercial buildings?
I think so. I do think that the potential in multifamily is really good. The systems tend to be pretty straightforward and similar across the building sector in multifamily, especially across similar size multifamily units. And it can be installed pretty straightforward in those buildings. And they, it's a lot of fixtures, a lot of showers, so the hot water usage is there, so the systems are usually pretty big and there's lots of use to recover. That is very similar to some commercial buildings. So certainly hospitality buildings, definitely loops within buildings that are maybe more focused on things like showers and things like that tend to be higher usage. The savings numbers, the pure dollars per year, are just going to be smaller in small systems that are really designed to keep a handful of bathrooms hot. And so the potential might be smaller there, and depending on how what the actual cost is for this system, it may or may not make more sense to spend your money elsewhere. I will say that the thing that is pretty attractive about this controller is that if the system is pretty straightforward, the install is pretty cheap and pretty quick. And so even if the savings aren't huge, if you can save 30% thermal and 90% pump, and the install only costs a couple hours, it's a pretty straightforward program design that could be implemented in a wide scale of buildings and see some pretty good savings.
Okay, and then have another question. Do you have specific recommendations around training building operators about this control so that they don't just override it at the first comfort issue, but actually troubleshoot to try to determine whether or not it's actually the control at fault or some other underlying issue?
Yeah, I think it is definitely an important issue to understand. And so we didn't specifically try to train the building operators for this project. So we don't, I guess I won't say I have specific firsthand examples of the best way to go about this, but it really is making them aware that there are options that aren't just to turn it off. So the controller does do a pretty good job of understanding when hot water is being used and never making the system sort of unusable. And so ideally the system can handle itself for the most part. But there are those parameters that can be adjusted, and the controller's manual and documentation does a pretty good job of explaining them. But it is really just about teaching whoever is in charge of that system that this controller is now installed, and if you have issues, here's how you troubleshoot it, and here's what the options are. And really getting them to understand how it works, which can be a difficult task at times, but as I said, the manufacturer's documentation is pretty good. So I think that's a good starting spot.
Okay. Well, thank you for that answer. I think that's all the questions we received. So now I'm going to turn it back over to Mary Sue to finish up this webinar.
Great, thanks. If you do have follow-up questions about this research after the webinar, I'm sure that Ben will be happy to hear from you. Just email him with those. One of the things I wanted to mention is that this webinar is being recorded, and it will be available as well as the final report. They will both be available on the Department's Applied Research and Development webpage in a few weeks. When available, you can link to them from either the webinar quick link or the card search quick link that are indicated here by the arrows on the slide. You also should know that if you haven't done it already, there is a handout to today's webinar that's available in your GoToWebinar panel. You can download, which is the slide set. And it's an annotated slide set. This R&D page that is up right now has a lot of other additional information related to the CART program. and the card projects that you might want to check out. And the webinar address is at the bottom of this, or the web address is at the bottom of this slide. Finally, well, actually, could you forward the slide, please? You didn't forward. Okay, there we go. It's at the bottom of this slide. So thanks for participating today. We appreciate your interest and the results of card projects. And before we leave, I wanted to mention a few upcoming card webinars. On February 22nd, the Minnesota Technical Assistance Project will discuss an often overlooked opportunity to reduce energy use in industrial facilities by replacing pneumatic power tools with direct electric motor-driven tools. On March 14th, the Center for Energy and Environment will report on 2 approaches to improve energy code compliance of individual newly constructed commercial buildings through tools and also through technical assistance to building design, construction, and code enforcement professionals. And then on March 28th, the Center for Energy will be back again to review the results of a project which sought to improve operating performance of residential high-efficiency condensing boilers through quality installation and retro-commissioning. Announcements about upcoming webinars and other news related to the Minnesota Conservation Improvement Program can be found in the SIP newsletter. There's a link on this page to sign up for the newsletter if you don't have it, if you aren't signed up for it now. In the meantime, contact me if you want more information on these upcoming webinars, or if you have questions, feedback, or suggestions for the CARD program or for CARD webinars. Thanks again and have a great rest of your day.